Good evening, everybody. I'd like to welcome you here to the program tonight. Tonight we have the pleasure of hearing from Dr. Keri Hoadley from the University of Iowa to tell us a little bit about the Webb telescope. So please give it up for Dr. Keri Hoadley.
Thank you all. It's so nice to be here. And I apologize for missing last time, but I'm really excited to talk to you about JWST. And I'm going to really focus on, I'm going to talk about, you want me to take my mask off? Yeah, that would help? Okay. Well, I normally don't, because I personally don't feel very comfortable doing so, but I understand, it probably helps a lot more to see my mouth move, right? So I'm okay with that. Okay, so I'm going to talk to you today about the James Webb Space Telescope, or what I refer to it as JWST. And specifically talking about one of the really, really cool things it's going to do, and that's it's going to help us find the very first stars and galaxies that ever formed in our universe. And I'm going to tell you why that's really exciting for astronomers, and why hopefully you can be excited about that too. So here's my first image, and this is one of the first images that we got to see from JWST when it released a series of 5 of them back in July. So that actually wasn't really that long ago, only 2 months ago. But since then, it's released a couple of more. I'm going to show you those and talk you through those as well. Right, so getting into it, JWST is truly a marvel of human innovation and ingenuity. It's the largest telescope that we have ever, as humans, sent into space. So, truly that in itself is a feat worth mentioning. Here, down below, are showing 2 people. There's 2 people here to scale with the size of this telescope, just to give you an idea of how big it really is. Right, and not only that, because of this telescope and how just fine we wanted it to be able to image the universe, this has led to some incredible feats and leaps in technology that have benefited us here on Earth. And one of the notable examples is that we had to make the mirrors so fine and so flat that we had to develop new ways to be able to sense light bouncing off of it, and we now use that in order to do and refine LASIK eye surgery, so to help people see better. So we use technology that was used specifically for this telescope now to help us, lots of people see better. And it also is really inspiring. So JWST, it took many, many, many years to get to the point where it came together to even look like this, and now is in space and operating. When I was in middle school and high school, this is when this was first thought of and conceived of. So I got to see it from a young age and being excited about science and space and be inspired by it. And years later, I finally got to go and see the space where it was built at a NASA center, and I got to take my own picture, a picture of myself, a little selfie, in one of its mirrors. So it really came full circle for me to see that final end product, and now here I am, a scientist myself, inspired by this instrument. So myself, I came to be really excited about space at a really, really early age, and it actually came about because of my own grandfather. I was very close with him, and he often brought myself and my sister to our local library. And there, I would run straight for the space section and try to learn as much as I could about our own planets. And I was really, really, really interested in these big gassy planets that we have in our outer solar system, Jupiter and Saturn and Neptune and Uranus. So that really got me excited about space in the first place. But what really, really hooked me was that when I was really little, I saw my first ever comet. I was younger than 10 years old, and I remember seeing Comet Hale-Bopp in the sky. Does anybody here remember seeing that? Yeah, it was like in the 1990s or so. It was incredible. And as a young child, it left a really big impression on me. And I also saw women astronomers on TV shows that I was watching. And I knew that if they can do this, then clearly I can do this. So it really inspired me to be able to, believe that I could be a part of this field. So I pursued it. I went to college and I got my very first internships and experiences working with professional astronomers. And the very first kind of projects I worked on actually involved using telescopes, and not just using telescopes, but building parts of telescopes. And I didn't even consider that that could be a part of my career. But I was instantly hooked on doing that and realized, like, there are some really, really cool things when you build your own telescope and send it into space, because you know really well how that telescope works. So then when that telescope takes data, you can understand what it's telling you really well, because you spend so much time with it before it ever sees other stars or galaxies. So I got the chance to have some really incredible opportunities through my career already. I've launched instruments into space on rockets. I have flown them on giant scientific balloons, and I'm working with lots of teams all over the world on trying to build telescopes that go into space, like JWST. So there's lots of cool things still to happen, but I'm here to talk today about JWST. So I'll take a step back and first give you a little bit of a glimpse into, whoops. Hold the play. It's not gonna play. So I have a video here, and I really like for it to play, but I don't know if it will. Okay, there we go. So astronomers, the way that we observe the universe is we observe the light that comes from everywhere in the universe to us. And this video is showing, well, it started with a view of the sky and is panning in to what looks like a pretty blank patch of sky. So the deeper and deeper and deeper you look, it turns out it's actually not black, but it's full of galaxies. So our eyes can only see so much. They show us the stars in the sky that we can recognize as patterns, as constellations. But when we build telescopes, large ones that allow us to look deeper, we get a much deeper view into the universe. So what that video ended on is this image, and this is the Hubble Space Telescope Ultra Deep Field. Up to a couple of months ago, this was the deepest image into the universe we had really ever had. So what this image is showing us are galaxies that are billions and billions of light years away. The light took billions and billions of years to reach us. But from what you saw previously, Hubble was looking at what it thought was nothing. So from nothing, it's revealed all of this light, all of the light coming from all these different kinds of galaxies. So in order to collect and see this light and to get deep, deep images into the universe, we as astronomers have to use telescopes. Our eyes are just not enough, right? So we use telescopes both here on the ground. We have, magnificent ground-based facilities, but also ones in space, like the Hubble Space Telescope that's been up there for 30 plus years now, in order to collect this light and to allow us to see the universe in ways our eyes can't see. So I want to take a step back and just, give you a brief review of what light is and what it tells astronomers about what we're seeing when we see different kinds of light. So the light that our eyes can see is a really particular kind of light. We call it optical light, and it's the blues and the greens and yellows and red colors that we see like on our shirts or in the light that we have in the room, or the exit sign as it appears red. Those are particular colors that carry particular amounts of energy with them. So our eyes just happen to be sensitive to those colors. But here, I'm showing you that this is just a really small part of all of the different colors of light, or energies of light, that can be carried by light, or what we might call photons, through the universe. And astronomers use this light to tell us a lot about what we're looking at. So for light that carries less energy, or has longer wavelengths, or much redder than what our eyes can see or pick up, that's really cold stuff. That's like the stuff that's cooler than stars and even planets. That's stuff that's found between stars and galaxies, like gases and dusts the stuff that might eventually make new stars. Now the light that our eyes can see, as well as a little bit of a range around there, that's where stars are really good at emitting light. So that's where we'll see lots and lots of starlight. And then on the really high energy range, the extreme range, this is where the extreme phenomena of the universe come in. This is where, like, when you get really, really close to a black hole, you're going to start seeing light with these kinds of really high energies. So what this tells us is that on this end of our, what we call electromagnetic spectrum, the spectrum of light, we have really hot, energetic stuff happening here. And then the redder we go, the more red we look, to even further red than the red our eyes can see, we're talking about really, really cold stuff. And so really low energies. So I like this little cartoon because it kind of shows all of this light is all traveling at the same speed. Now that's going to be key. Light has a certain speed, and they all travel the same way. But the red light is pretty chill and relaxed, and it's kind of low energy and moving, whereas the blue is really yippy and trying to keep up. It kind of gives you an idea of the kind of energies those photons are walking with, and that's analogous to how light acts. Right, so there's lots and lots of kinds of light. So how do we see all these flavors of light? All of them are going to tell us about different phenomena happening in our universe to try to understand the physical nature of the universe and our place in it. Well, we have all kinds of different kinds of telescopes we can build to do this. So we unfortunately can't build a all-for-one telescope. Unfortunately, the way that materials and cameras and mirrors work won't allow us to use just one big mega telescope to observe all the high energy light, all low energy light, and everything in between. So we sort of need to split up our telescope capabilities. But besides that, the Earth's atmosphere gets in the way of us being able to observe a lot of the different kinds of light we'd want to see in the universe. So Earth's atmosphere is really good at allowing optical light through the atmosphere, so all the light that our eyes can see, that's no problem. But you talk about it almost anywhere else, the higher energy light, no go. The atmosphere loves to absorb that before it could ever reach us on the ground. Some of the redder light as well, no go. We have water and stuff in the atmosphere that'll just block all that from reaching us. So we need a way around that. And so the way that we do that is we send telescopes into space. So a big motivation for sending something like JWST into space was exactly this reason, that Earth's atmosphere is really good at blocking the light we want to see with JWST. NASA is the U.S. Federal facility, or agency, I guess, that is responsible for launching our telescopes into space. So NASA sort of leads the drive, and the community calls their most ambitious and powerful telescopes that we build our great observatories. So since the Hubble Space Telescope was built and launched over 30 years ago, we have had 5 of these great observatories in space. So there's the Hubble Space Telescope, Chandra, which observes X-ray light, which is pretty high energy light. Compton Gamma Ray Observatory, again, really high energy stuff. And then Spitzer and now JWST, both of which are infrared telescopes. And these observatories just don't come about willy-nilly. Astronomers actually have to come together once every decade or so and come to a consensus on what are the really big pictures or the questions that we do not understand yet, and how can we try to build something like a new telescope to let us understand it better. And this is just an example of the one from the 1970s that basically conceived of the Hubble Space Telescope. So 1970s Hubble was dreamed of, and then in the 1990s it was launched. And from there, subsequently, each of the decadal surveys after that thought of one of these other great observatories. So 1980s came about with the X-ray telescope, and then we had our Spitzer telescope after that. JWST was thought of in the 2000s. So it took about 20 years to get from, and that seems to be a recurring theme as well, about 20 years after it's first conceived, we finally launched. So it gives you an idea too that these are very ambitious telescopes for the time. They take time to do, but when they do finally go, they reveal the universe in brand new ways, in really beautiful ways as well. All of these observatories historically have really tried to address fundamental questions that we don't know about the universe and we're trying to figure out. They all do them in very unique and different ways. These are some of the big questions we're trying to answer with these telescopes. How did the universe form and evolve? How did galaxies and clusters of galaxies form? Where do stars and how do stars form and evolve and eventually die? How and when do planets form? And then the big question is, how did life start? And are we alone in the universe? So these are really, really big questions, right? So each of these were designed specifically to tackle these in very unique ways that help us to better, get an idea of each of these, of answers to each of these questions. So I'm going to talk a little bit about some of the properties of JWST and how it compares to HST, or Hubble Space Telescope, which is one of the more famous great observatories that we still hear about and what we often hear is compared to JWST. So the primary mirror size of JWST is 6.5 meters. Again, here are a couple people on the ground to show as a comparison to the just huge size of this thing. But the Hubble Space Telescope has a primary mirror size of about 2.5 meters. It's about as tall, as an average person. So it's much larger, which means that it can collect a lot more light. You can think about the size of our telescopes comparing to like how much a bucket on the ground versus a glass on the ground can catch water. So the bucket is going to catch much more water because it's much wider, right? So if a rainstorm rolls through and it rains into the bucket and the glass and the rainstorm leaves, you're going to have way more water in your bucket than your glass. And that idea is analogous to the size of our telescopes. So the larger the telescope is, the more light that can be collected by the telescope. So what that means is we can see fainter and fainter things. It means we can see deeper and deeper into space. So we wanted JWST to be really much bigger than anything else we've ever had, so we can see deeper and deeper into space, and so farther and farther away galaxies. JWST is also optimized to look at light that our eyes can't see. So if we think about the spectrum again, our light spectrum, and the light that our eyes can see is this rainbowy color. JWST is looking just redward of that, so light just a little bit lower energy than it. And by comparison, Hubble Space Telescope is really good at seeing light that our eyes can see. So this blue color here, bar, is where Hubble Space Telescope is designed to look. And JWST, you'll notice the bluest or the highest energy light that JWST will see is really the reddest light that Hubble will see. So they may have just a little bit of overlap, but not really all that much. So it's looking at light that not even Hubble is designed to look at. And then in the observatory itself, so I'm showing and talking a lot about the primary mirror here, how large it is. But behind that primary mirror, we have instruments that have cameras on them that then record the light that is captured by this telescope. And so in here, with this module that carries those cameras, we have different kinds of instruments that give us different ways of looking at the universe with this telescope. So here's the names of those instruments. I'm going to talk a little bit about, I'm going to show a lot of images that are primarily from the NIRCam image, or NIRCam instrument, which is really taking beautiful infrared pictures of the universe with this telescope. And then, again, like all the great observatories before it, JWST is slated with some key scientific goals, including finding the first stars and galaxies that formed in this universe, understanding how the first galaxies formed in the first place, looking at how clouds of gas and dust that are often found in galaxies collapse to form stars, and then from there, how do solar systems ultimately form, and can we identify life elsewhere? So these are really big questions, right? And this telescope is actually doing a pretty good job already of trying to address them. Okay, but before I move on, I'm going to say that I'm going to focus on this very first question. I'm going to give you a little bit of backstory to it, starting with the beginning of the universe, right? So we're searching for the very first stars and galaxies. So I want to set the stage for where we think those first stars and galaxies happened and how we're going to try to find them. So here we know, or we suspect, that the universe has started with a bang, or particularly we call it the Big Bang. And our first glimpse of this start to the universe happened back in the 1960s when radio astronomers accidentally observed the glow of the birth of the universe. So this fiery beginning to the universe, we see a temperature spread throughout the entire sky, looking everywhere we can in the observable universe, and we call this the cosmic microwave background. And it's basically this first wall when the universe has become just transparent enough to let the first light through and to allow us to see this first look into where the first particles formed. But we'll get back to that, because I'll show you where we think that happened in this timeline of the universe. So if we start here with the Big Bang, I'm going to run through this little cartoon that highlights some of the major events at the beginning that started the universe, or we suspect did. And here we're going to have a time scale, and this is basically time of 0. It's a really, really, really small number, and there's also going to be temperatures associated here. And for all intents and purposes, these temperatures are going to be extremely hot, like so hot that we've never seen these kinds of temperatures in the observable universe to this point. So here, at basically time of 0, the universe and everything in it went from an infinitely dense, infinitely small point, what we call singularity, and started to expand outward. And it expanded outward incredibly rapidly. It went from basically time of 0 to almost no time at all. This is way less than a second though, right? So we went from nothing to something, and that something was about the size of a beach ball. So, about the size. And we're holding everything that exists in the universe and something about that size. So at this point, we're still incredibly dense, incredibly hot, and this is where the universe continues to expand out, right? So it started with this initial huge expansion and has expanded since. And during that expansion, when you expand out, you're allowing things to stretch out. You're allowing room to begin to form between things, and so it begins to cool. And so it's now getting to points where things can come together and other forces of nature can start taking over. So like forces that hold particles together can start taking over and forming the first particles that make up things like protons and neutrons, the elements that we see in the universe. So we have the very smallest particles forming first, followed by the very simplest particles that we see in our universe, like hydrogen and helium. So by about 1,000 years after the Big Bang, we have this, the end of the age of nucleosynthesis. We have hydrogen and helium, all of the hydrogen and helium, well, all of the hydrogen and a lot of the helium that we have today in the universe formed basically from about 5 minutes after the Big Bang to 1,000 years after the Big Bang. So actually kind of incredible. So these are the first two elements in our periodic table we have formed in this chaos of the time. Right, so after then, we have this time where we're fusing together hydrogen and helium, it ends, and we get to a point where we're in the age of ions. So now everything is beginning to spread out enough, but it's still really, really hot. So we have basically these protons and stuff floating around and very energetic, not able to capture electrons that would help neutralize them. So it's a really chaotic time until about 3,000 years after the Big Bang. We can cool down enough for things like hydrogen and helium to finally capture electrons, and by doing so, emit light. And so, in a way, this light that we're seeing is like that time when we're going from a very chaotic, really hot time to a time where, okay, things are just cool enough now in the universe to start, capturing electrons, emitting light, and releasing it out into the universe. So this is that cosmic microwave background, and we're seeing everything beyond that, earlier than that, we cannot see because it's just too dense, it's too hot, and there's no way for that light to escape us. So it's right here at about 3,000 years after the Big Bang. This is the earliest back we can really see, and this is our main clue that there was something beforehand that happened to the universe to make it go from this really incredibly dense state to what it is today. But shortly after that, or I shouldn't say shortly, because it was actually quite a long time that it took for this to happen, the universe is still continuing to expand, and it's releasing energy in the form of light, so it's allowing itself to cool. And so now these particles, hydrogen and helium, are cooling. And when they cool, they can kind of come together. Before they're too hot, so they want to, be bouncing around everywhere else. And when they cool down, they can begin to condense together. And so they begin to condense through these kinds of overdensities that appear in the universe from this mysterious kind of matter you might have heard of called dark matter. We suspect does not interact with light for some reason or another, but can be gravitationally bound, and clumped together itself. So hydrogen and helium begin to flow into these places where there's lots of other matter due to the pull of gravity, and eventually come together to form stars and galaxies. So the age of stars and galaxies, we think the first stars and the first galaxies might have formed somewhere around 300,000 years after the Big Bang. So that's where we think the first stars and galaxies are going to start. So at about this point, all the stars that would have to form from stuff like hydrogen and helium. Okay, we're going to point out in a little bit why that might be a problem, but I wanted to first point out this particular periodic table of elements, because this is like the astronomer's periodic table of elements. It points to where the origin of all the elements that we know about comes about. So hydrogen is all from the Big Bang, a lot of helium, but everything else is formed from stars. Everything else comes from stars in some way, whether that is stars like our sun, or really massive stars colliding together or exploding at the end of their lives. All the other elements were formed in stars. So I point that out because all the stars that we have ever observed have other stuff besides hydrogen and helium in them. So for the first 100 to 300 million years or so, all we had was hydrogen and helium to form our stars. But at all other times after after that, there's been other stuff. There's been carbon, like we're made out of carbon, a lot of carbon, and oxygen, like the stuff we breathe. Those are really commonly found in other stars, including our own sun. Right, so we have to take a step back then in order to try to find and identify the first stars and figure out when they first formed. We have to think about, how do we form stars in the first place, or how do we think we form stars? So I threw up here the latest image from JWST. It was released just a few days ago, of the Tarantula Nebula, which is found in a galaxy that's really close to us, the Large Magellanic Cloud, and it has lots and lots of star formation happening right now. And it's showing here a Hubble Space Telescope view of this same place, and here's JWST. And you might, I don't know if you noticed, but I think they look quite different. One looks like really chaotic and very white, very bright, and the other is peering and seeing stars that were hidden in this view. So what's important about this is that JWST, remember, is looking at light redder than what Hubble can see. It's looking into the infrared. And so what it's able to do is it's able to see past some of this warm, very warm stuff that's blocking the view to the newborn stars being formed inside of these dust clouds. So whereas Hubble is looking, really you can think about it as like the surface of this star-forming cloud, JWST is able to peer into it more and reveal these clusters of stars forming. And here's another famous, the beautiful Carina Nebula image that was released from JWST, showing a star-forming region in our own galaxy. And also, again, peering into the cloud and revealing stars that we didn't even know were there before, because we'd never seen them with something like Hubble. So this is actually really, really important, an important aspect of JWST, to try to understand how stars form from these clouds of dust and gas, and it's allowing us to peer into them to reveal newborn stars in our own local galaxies. But, okay, from that, how do we then think stars form to help us figure out what the first stars might have looked like? So we start with a cloud of gas and dust. And this is just a little illustration meant to show you and guide you through how we think a star ultimately forms. So we'll start with this cold cloud of gas, which is made up of hydrogen and helium and gas molecules and dust. And eventually, enough of it comes together into a small enough volume that gravity is now the dominant force. It's going to take over and it's going to want to smush all that material down into one point. So when that happens, this takes time. So as this cloud is collapsing onto itself, at the center of this cloud, a new star is now forming. We get enough matter that is clumped together to begin to ignite things like fusion, or beginnings of, to form a star. But again, this takes a lot of time. It takes up to 100,000 years. But a really key part of this whole collapse is that we have hydrogen and helium in our cloud, but we have other stuff as well. We have dust, and we have carbon, and we have oxygen. And it's these other things, these other elements, that actually help that cloud to cool to form the star in the first place. So again, remember, if it's too hot, nothing's going to want to come and clump together. It's going to have enough energy to like disperse away and move away. But when it's cool, it has very little energy, and so it'll just kind of like go with the flow. It'll clump together and allow gravity to win. So if we don't have these other things available to us, if we just have hydrogen and helium, like at the beginning of the universe, then how do we get a cloud cold enough to clump down into a star in the first place? That is an answer we're not really, really know. Yeah, it's actually kind of one of the bigger mysteries in our field. The things that we do know or suspect is that the first stars likely only have these two elements to form from, with a very trace amount of lithium, which is only just a little bit heavier than them. Whereas something like the sun is made up of primarily hydrogen and helium, but it has just enough of this other stuff, oxygen and carbon and iron, to really follow our theories of star formation pretty well. So the first stars, not so much. But by their size comparisons here, the size shown here, if this is like our sun, sort of like a scale representation of our sun, our suspicion is that these first stars were probably extremely large and extremely massive in order to compensate for not having those things to cool them down. They probably had to hold just a ton and ton of hydrogen and helium to ignite. And because of this, they probably died really, really fast. So they probably lived really fast lives. So the sun, for comparison, we expect it to live about 10 billion years, and we're about halfway through that life cycle now. So the sun and the earth and the solar system have been around about 5 billion years or so, and it's got another 5 billion years left. But the first stars, we suspect, probably only lived about 1 million years or so. So really rapid lifetimes. So if we were forming the first stars, initially from the hydrogen and helium clumping together, and say we had, good number of them forming all at once, they probably lived in a really chaotic, explosive time where things were forming and then almost immediately running through their fuel and dying. So they might have started expelling new elements like carbon and iron and oxygen out into the universe really rapidly. So the first stars that formed in the universe were both massive and hot, and so astronomers can use that clue to look for the kind of light we suspect that those stars emit. So if we have a really, really cool star, its temperature is kind of low, and it might emit like redder light. So it might emit light that's kind of like here. It kind of peaks around like this redder color. But if we have a larger, more massive star, it's going to be a lot more hot, and so it's going to produce light that is much more blue, a lot more energetic. It's hotter, so it's a lot more energetic with the light it's emitting. So astronomers can look for that particular light, and also what you might notice is that these cooler stars, the light they're emitting is kind of like at a lower level than the more massive ones. They're emitting a lot more light. So they might also be emitting just like a lot more luminous light than cooler stars. So how is JWST going to then observe these first stars if they shine really brightly at this bluer ultraviolet light and not really the red or infrared light that this telescope is designed to look at? Well, there are two key things going on here. We're talking about stars at the beginning, very beginning of the universe, so 300,000 years after the Big Bang. And first thing to note is that light doesn't arrive at us instantaneously. It takes time. And this is because the speed of light. We know that light has a speed. The universe basically has limited the speed of anything in it to the speed of light. So it's the fastest we can travel through the universe. A good example is like I can take a selfie of myself in a mirror. That, the light reflecting off of the mirror and going into my camera, that happens to me in my brain instantaneously, but really it takes, fractions of a second to happen. If we look at the sun in the sky, actually the light leaving the surface of the sun and reaching us here on Earth, that takes 8.5 minutes. And the galaxies that we saw in the Hubble the deep field, that light arrived at us billions and billions of years after it was first emitted. So everything that we see, from the reflection of ourselves in our mirrors, to you looking at your neighbor, to the sun in the sky, and to the furthest galaxies, this all comes from the past. It's very weird to think about, but it's really because light travels at a finite speed. And at the same time as that, light's taking time to travel, the universe is also expanding. So, okay, one way to think about this is if we had two galaxies, they started kind of closer to one another, and then one galaxy released a photon, some light, at one time, and it was traveling towards its neighboring galaxy. But at the same time, the universe is expanding, so the space between those galaxies is stretching. And so that light is also stretching in the space. So by the time it finally gets to the second galaxy, it's actually stretched out in wavelength. So if it was released as a blue light, it was stretched out into a red light. So the way that we astronomers like to think and talk about it is we talk about it as a redshift. So we're seeing galaxies way back in the past have these particular fingerprints in their light signature. So if we spread out their optical light into like the rainbow colors, we might see particular features or colors missing. That tells us a lot about what is in the galaxies, whether that's like hydrogen or oxygen or anything like that. But we can use this kind of fingerprint and look at galaxies even further away and see that whole spectrum. We identify the same features, but now they've been redshifted. They've been shifted to redder color. And so we can use the shift to tell us about how far back in the past we're looking to those galaxies. So the first stars that might have formed might be outputting a lot of light here, the really, really blue color. But over billions and billions of years, that light is going to be stretched out with the expansion of the universe. And by the time it reaches us, with JWST, it's going to fall right into the place where that telescope can observe it. So that's how JWST is going to target these very first galaxies. It's relying on the fact that the light that we expect the first stars to emit, this really blue energetic light, is going to be stretched out into the place where JWST is able to observe. And we have done this and targeted, trying to look back in time for these kinds of stars with lots of different observatories, from ground-based ones to with Hubble as well. But JWST here is really bringing us even further than anything else we've done before. Okay, now a little bit of like a little series of how things have gone for JWST since its initial launch. So JWST launched last Christmas. Did anybody watch that that's here? Nice. Awesome. Yes, I love it. I woke up extra early to watch it. I'm really happy I did, but I don't normally get up at like 6 a.m. Yeah, this was really exciting. It was a beautiful launch. And this video here, this little GIF, is the very last image we ever have of this telescope. So all the images we have of the telescope itself on the ground, or like when we were building it up and getting it ready to go, this thing has traveled out 1 million miles from us on Earth, and we're never going to have, quite that kind of picture of it again. So this is our last view of it before it went on its way. For the next couple of months after that, it traveled from Earth out past the moon and into this stable orbit called the Lagrange Point. It's where the Earth and the Sun have about an equal gravitational pull on the spacecraft. And that's where it lives now. So it's pretty far from Earth, the Earth and the Moon and the Sun. And that actually is a good thing because especially the Earth and the Moon would glow really, really, really brightly in the kind of light that this telescope sees. So it would be a big source of like contamination and extra light that we don't want. Along the way, it underwent a series of deployments. It basically like unfolded itself, released these sun shields, and then when it was traveling, that big, beautiful primary mirror we saw on the ground, when it was all nice and unfolded, it was all folded up for launch because it was in a rocket fairing, and then so you can see the wings of the telescope unfolded itself here. Yeah, and then the second mirror that it's going to see sort of came down and snapped in place. And everything went beautifully. This is one of the first images we got from the ground of the telescope after it unfolded itself. And this was to give astronomers an idea of, okay, where are we at and what do we need to do to get this thing ready to take scientific images. So this is the very first picture. What it's doing right here is it's trying to look at a star. So if everything went really well, we should have seen all of these little hexagons here that make up its mirror. They should have all been glowing with the same intensity, but we're only seeing one of them, right? So we had kind of a long way to go. The process for that, shown here, is that basically each of these little hexagons have their own way of moving around. So they might have been like all kind of out of place at first, but astronomers on the ground could help guide, when they were looking at a star, that star into a particular point, the center of all those hexagons, and then in theory they should all be lined up. Right, so this is the first image of JWST. So this is what it basically started with. This is one star. It's not seeing one star. So it told astronomers that it was way out of alignment, so they had quite a ways to go. Oops. I wonder if this will play. It won't. Oh, that's too bad. I had a little GIF that showed it basically following that little animation you saw. It moved all these spots here into basically a nice hexagon pattern and then moved them all to the center. But this is the final image it took to verify its performance. Like once all those things were all lined up, and astronomers were like, okay, let's take a deeper image to make sure that this is actually nice and crisp and clear like we want. This is what I saw. And this is really exciting. I'd say astronomers everywhere were blown away by this image because it shows the star. More specifically, it shows this pattern around the star. You might see 3 tiers of spikes and then a couple of extras showing up. Astronomers, optical scientists expected this pattern for a nearly perfectly aligned telescope. So they got JWST set up much better, and like with a more crisp image than we actually accounted for or planned for. So we now have a telescope that performs better than what we expected, which is an astronomer's dream. In this image as well, I have a note here, that in the press release of this image, JWST's diffraction limit is approaching its theoretical limit. That's basically saying that like this is the best performance we could have expected from this telescope. And of note is that in this image, which was only a couple of minutes long to verify the performance, we're seeing galaxies that we never even knew were there. We had other infrared telescopes look at this same star before, but the quality of it is just so much better. I'm going to show you a comparison now with one of the other great observatories, infrared observatories. NASA launched the Spitzer Space Telescope. This is the same star. So this is the star with Spitzer, and that is it with Hubble. And as you might see, we're seeing other features as well, other galaxies in the background that even Spitzer, our previous great observatory in the infrared, never saw. So it's really a huge step up. Okay, so now I'm going to go through a little bit of like what we're learning so far, and what kind of the really exciting results have been to date. So here is the famous first image that was released out of the White House. Did anybody watch that by chance when it happened? Yeah, awesome. Oh, wonderful. I love it. That was really exciting. I was actually away, but I watched it with a couple of my colleagues. We were working on our own telescope at the time. But it was really exciting to see this first view. Our first thought was that it looked like, you know, a ramped up version of the Hubble Deep Field. And it actually kind of is. So in this first image, what we're seeing are many more galaxies, galaxies approaching the beginning of when the first galaxies may have formed than we thought we would in this kind of image. So of note is that this galaxy, or this image, was only taken in about 14 hours. And I say only, that's a lot of time. Still, it's like over half a day. But remember the Hubble Deep Space Field, the deepest look we had had to that point, that took like over 2 weeks to make. Yeah, so we're going from having to stare at a blank patch of sky for weeks to less than a day, and we're getting even deeper images into the universe. So that was heartening to me as an astronomer, to see that kind of power behind this telescope. This is not showing up super well, but this is meant to show that we are building on this first image, a deep image with even deeper ones now, and we're beginning to build like big patches of build up big patches of blank sky to reveal hidden galaxies, or galaxies that are, you know, approaching the edge of time. So we have more deep fields than we've ever had before, even with something like Hubble. And one of the main programs doing this is called SEERS. They're specifically looking for the first galaxies and stars that formed in the universe, and they're beginning to put out like these enormous mosaics of the sky that show galaxies that are revealed, much like the Hubble Deep Field was taken. They're looking at what we thought were blank patches of sky and revealing thousands and thousands of galaxies. They're revealing that there's really no blank patch of sky, truly. So from these kinds of surveys, though, we're already building up new catalogs of galaxies in ways we've never been able to do before. So up until this point, we have had, you know, really good glimpses of galaxies near us. We've been able to see what their colors look like, what their shapes look like, and infer some important properties about them, like how much stuff are they made up of. That we can, you know, find relationships between particular information about galaxies to help us better understand them. But we've never been able to do that with galaxies, you know, so far away before. But now we're seeing so many of them that we're able to build these brand new catalogs, basically of like, you know, for example, how much mass is found in a galaxy versus how much time has passed. And so we're beginning to fill in the space of galaxy evolution that we've never had access to before. And we're already beginning to see both similarities and differences between galaxies we see today and galaxies that were around, you know, billions and billions of years ago. And then we're also seeing really interesting galaxies and clusters of galaxies that are maybe not what we expected, or, you know, nice surprises. So here I want to point out just a couple. This number 2-1 shows this large galaxies and then a bunch of series of other galaxies. And this is really interesting because it looks to us astronomers a lot like the sort of filamentary material we thought that the original gas in the Big Bang might have clumped down into to form the first stars and galaxies. You might not see like the underlying gas that might be here, but potentially you're seeing little hot spots where enough stuff has come together to form stars until light leaves up, potentially. And then number 4 here is really cool. JWST accidentally caught a star exploding in a galaxy a couple of billion years ago. So finding these are actually, to this point, have been quite rare. And we build particular kinds of telescopes in order to look for these because they tell us a lot of information about how far away the stars and the galaxies might be, what kinds of stars are hosted here, and stuff like that. But it just happened to catch one, go off at a particular time when it was observing this. And we suspect that these kinds of explosions might happen more often than we thought. It's just that JWST is so sensitive that it can see them and is probably going to capture way more of them. Okay, and then probably one of the coolest and most exciting results is that in the most, we're identifying galaxy candidates now that we think had formed or are emitting their light much shortly after the Big Bang. So at these times after the Big Bang when we thought the first galaxies should form, and they may have way more stuff in them than we thought they should. So of note here is this galaxy called Maisie's Galaxy. So it's found, let me try to trace this here. It is found about here in this patch of sky, and we're zooming into about here. So this guy here, showing this little dot that's actually a galaxy in this huge image here. And it's a galaxy candidate at about 300 million years after the Big Bang. And based on the colors we've seen from it and how bright it is, we think there's way more hydrogen and helium in it than there should be. So this might be a test of some of our fundamental assumptions of how the first galaxies and stars formed. But with the caveat that this galaxy still needs to be confirmed at this age. So just based on JWST information so far, it seems like a really good candidate for being one of these first galaxies we think should have existed in the universe, but might, but being extra careful and they need to follow up on it. So that might change. You never know. Okay, thank you. That's all I had. But thanks so much. Awesome. Yes?
That last pattern that you showed, that had about 100 spots. No, not that one.
Oh,
That.
this one.
Are those each stars or each galaxy?
Each of these are galaxies. Yeah, so I'm trying to figure out the clicker. Great, so yeah, so all these different shapes we're trying to show here, and the colors, these are all different, galaxies. So they're all made up of like billions and billions of stars themselves.
And the colors that they all look either blue or yellow or white.
Mm-hmm.
Aren't there any red ones in there?
On this end there's a little bit. Yeah, but there's a red one back here too, down here. But yeah, they're all right. Yes?
Can you estimate the size of our galaxy and put it on that chart you have there?
Oh my gosh, that's a good question. We are probably in like this range here.
So fairly large compared to what you've got.
Yeah. Our galaxy is actually quite large. It's the second largest galaxy in all of the closest galaxies to us. But has anybody heard of the Andromeda galaxy? Andromeda? Yeah. Yeah, that's the largest galaxy close to us, right? So we are really close to the size of Andromeda, but maybe just a little bit smaller. Yeah.
The information that's coming back, is it considered massive proprietary, or is it being sent out into the world for other agencies, other countries to take a stab at what is happening?
Yeah, it's anybody and everybody that wants to use it. So there's a place where NASA stores it. It's called the MAST Archive, M-A-S-T. And if you look up JWST data or images, it provides anybody that wants it with everything it's imaged so far. Yes?
How often or how many galaxies are spiral-shaped like ours?
Oh, that's a good question. It depends on how far back in time you look. It takes time for a galaxy to form that spiral. It has to do with, as stuff sort of collapses down, it's beginning to spin up, and so there's this.
It's like going down the drain.
Exactly, that's exactly right. So so when you get closer and closer to the drain, it gets faster and faster, right? So as that happens, the stuff behind it sort of lags and begins to create this sort of beautiful spiral pattern that we see. And that takes a little bit of time, so maybe towards, a couple of billion years after the Big Bang, that might have became more prominent. I think that astronomers are starting to see that when we're looking back at galaxies like 5 or 6 billion years ago. But it might not have been very common. It might be more common like today, or maybe a couple of billion years in the past.
So would that suggest that the spiral galaxy is on its way to becoming a black hole?
It is. That's a great question. So the stuff near the black hole may eventually become part of a black hole, but there are other things that happen before a galaxy can actually spiral into itself into a black hole. Like it has neighbors that sort of disrupt things and move stars and gas around, so it kind of prevents that from happening. It's like a tension that like things maybe want to spiral in, but then other things disturb it and keep it from really doing that. Yeah, of course. Oh my gosh.
Who designed and launched this thing?
So a whole bunch of NASA engineers and scientists designed it, and then the launch was NASA and the ESA, so the European Space Agency. It actually launched from the European Space Agency spaceport in South America. It was basically a global effort. It has, I showed some of the instruments, or I showed that one slide that showed, the instruments in it, and one of the instruments was made in Europe by some European collaborators and scientists. There's a big stake in this telescope from agencies all over the world.
Russia have anyone?
No, I don't think so. Actually, no, I don't, because I think Russia is making a different telescope. Yeah. Yes?
Thinking about the Drake equation, now that we can see in another whole spectrum, roughly how many orders of magnitude more star system candidates do we think exists in whatever the universe consists of?
Oh yeah, so many. We're discovering, in each image we're discovering thousands of galaxies we didn't expect to be there. So that already, it's already a magnitude of at least 1,000, even more. But the Drake equation, that's excellent, excellent question, because that's really made to set us up to think about the likelihood of finding intelligent life in our galaxy. And even in the most pessimistic case of that is we're the only ones. But considering other galaxies, if you think of the pessimistic case, the pessimistic case means that there's got to be something in each of these galaxies. So it's really, I love to think about it. But yeah, when I first looked at, let me go back to this image. When I first saw this image, my first thought was, I can't actually conceive of a universe where we are the only life here. With all of the chances to form life somewhere else, and all of these galaxies made up of billions of stars, it just seems so incredibly unlikely. do you mean?
Well, if it came from a singular, extraordinarily dense pinpoint,
Yeah.
what's so incredible about only having one planet with life on it?
As a scientist, the probability of that, given the number of stars and the number of galaxies in the universe, just seems so unlikely, even in the worst case scenario.
It all seems unlikely.
It does, yeah, absolutely. I can't argue with that.
Unlikely that there is other life, or unlikely that there isn't?
Isn't. Yeah. There's just so many chances, I guess. Yes?
What was the agreement of calling it JWST instead of Webb, so you could compare it to Hubble and, just...
What does it stand for?
It stands for James Webb Space Telescope or something.
Right.
Why don't you just call it Webb so it can be compared to Hubble?
No, yeah, I understand. So I think most of NASA and space agencies do call it Webb, but I choose not to because of the history behind Webb, the person. So Webb, I don't know, you might be more familiar than me, but Webb was a politician in the United States, and he was administrator of NASA during the Apollo missions. But during that time as well, there was a mass purge of LGBTQ NASA employees and federal employees in general that in our field makes people that identify that way very uncomfortable. So I choose to go with JWST instead of Webb, just to try to be more inclusive to my colleagues. Yes? Yeah, sure.
What is the mechanism for controlling the telescope to stay pointed at one star or one location?
No, that's a great question. So I think it's a combination of two things. Oh, sorry. So I believe that it may have rotary wheels on it, much like a lot of spacecraft that we send up. Like Hubble Space Telescope has these as well, where it's basically little gyros. And gyros, like a gyroscope, is really stable. Even when you try to move it around, it can stay in one point. It's the same idea. It uses angular momentum to keep itself in place. But it also has propulsion on it. It has a whole bunch of fuel on it and little jets that help keep it pointed really well. So when it's staring, it's also, it's moving around really, 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 just a little, we call it jitter. There's a little bit of movement happening, but we try to keep it small enough that we can, keep these images nice and crisp. Yes?
We found so many new galaxies. Have you found any evidence that there is another sun and there are other planets out there in the universe?
Yeah, we have. So a little bit of both. So we have found other stars that look really, really similar to our own sun. Around those stars, we're still trying to find planetary systems around them, and some of them we have, but they don't look a lot like our own solar system. They look quite different. And we have found over 5,000 exoplanets, planets outside of our own solar system at this point. And JWST is going to be looking at them as part of its program in order to try to understand what those planets are made of, compare them with the atmospheres of our own planets, see how they're similar or different, and look for signs that life might be present on those planets.
Thank you.
Yeah, of course. Yes?
Is space dust like household dust?
I love that question. It's so good. Kind of. Is space dust like household dust? That's a great question. I love that. So when we talk about dust in space, we're really talking about really small molecules or little chains of molecules. So you might think of the dusts under your bed or something as chains of hair and stuff kind of built up on one another. In a similar way, the dust in space is like that, but on a much smaller scale. So probably, at the size or smaller than grains of sand. Yes.
I wanted to ask if the universe is still expanding, and if it is, do we have any way of projecting how long it might continue to expand?
Oh, that's a really great question too. So the question was, do we think the universe is still expanding, and if so, can we project how long it'll continue to expand? The answer is yes. The universe is still expanding. We are able to measure that by measuring little markers. We look for exploding stars, like the one we saw in the previous image, that give us an idea of how far away those stars are, and we can estimate, like, the distance between us and that galaxy that the star exploded. And what we're seeing is that the closer galaxies to us that are not gravitationally bound to us, like Andromeda and the Large Magellanic Cloud, those galaxies are moving faster away from us than galaxies closer to the beginning of time, which suggests that the space has expanded more. And in fact, it's increasing. The expansion is increasing for some reason. The reason for the expansion, we don't know. And this is what we call dark energy. There's this underlying energy source that is stretching the space of the universe. The biggest question in cosmology now is whether we're going to continue to expand, or if we're going to stop, or if we're going to reverse course, if we're going to basically do U-turn and contract. So astronomers, we have, we don't know what's going to happen at the end of the universe, whenever that is, if that is, but they do have ideas where we might go if one or the other of those scenarios happen. So the most likely course right now, we think, is that we're going to continue to expand, but the expansion is going to happen at a rate where everything in the universe is going to basically cool down to a point where no more stars are going to form, all the black holes are going to evaporate, and we're just going to have a very cold, dead universe. Sounds very bleak, but it's going to take a really, really, really long time to get to that point. But if the universe does continue to accelerate its expansion, we could get instead to a point where we're basically ripping galaxies and stars and planets and people apart, right? So, well, not people. We'll be long gone by then. Yes?
So back to Earth, the relationship of the telescope to Earth, because we're revolving around the sun, is the relationship between us and the telescope always the same, or does it change?
That's a great question. So where the telescope is, it's further away from the sun than the Earth, and it always stays that way. And it's always so that the sun and the Earth are like basically in a line behind it. So it's going to like orbit with the Earth. Like if you think of everything on like a line, so the Earth, the sun, the Earth, and the telescope, as the Earth rotates around the sun, it's going to stay in this line. And it's going to always look away from them. Yeah. Yeah, of course. Yeah, thank you so much for having me. I appreciate it.